Hello and welcome back to another video in the game development series. This VMK is going to focus on adding a node texture to our game engine. With a node texture, we'll be able to incorporate different kinds of textures into our existing objects that we've predefined. So we've got a triangle, a flat grid, and a house in our scene, and now we're going to be able to add the capability to texture each of these objects with whatever texture you would like. Now this texture module is going to be broken up into a series of VMKs to split up the work. This first VMK is going to focus on creating the NodeTexture class. Now the NodeTexture class is going to be responsible for loading a texture file from a file into memory and being able to manipulate the pixel data in memory. The next VMK is going to show you how to modify the scene class so that we can incorporate this node texture which we're going to be creating. Lastly, we're going to go into our object library and modify the triangle class, the flat grid class, and the house class so that we can go and render things with a texture. So let's get started. First thing we need to do is go into our game engine and add some .h files and .cpp files into our scene lib. So we'll select scene lib here, right click and go add new item. We're going to add a CPP file and we'll call it NodeTexture. And we'll repeat this for the .h as well. Okay, let's start with the .h file. At the top here, we include core.h, which will have some important information that we'll be using, such as the error handler. So we need to include that at the top. Then we have our class called NodeTexture. We have a constructor, which we pass in the error handler pointer. We have a virtual destructor, and then we have two public functions. We have a load and a create texture OpenGL. The load will call by specifying a file name here as a parameter. That's going to go and try to load a specific file from our hard drive into memory. We have a create texture OpenGL, which will call to do the necessary processes so that OpenGL will be able to work with the texture that we load up here. Internally, we have a couple private functions. We have a loadTGA function and a flip image. The loadTGA function is going to be used to load a TGA file from disk into memory. If you want to support other kinds of texture files like JPEGs or PNGs or anything else, you'll have to go and create your own load function. Flip image is a generic function that we use so that if the texture that we're loading in is flipped in memory, we need to go flip it back so that the orientation is correct so that when we render it, we'll render it with the right side up. I'll talk about this in a little bit. In our variable section, we have an unsigned integer for the number of bits per pixel that the loaded texture contains. We have an unsigned integer, which is an ID number, and we use this ID number to specify which specific texture we want to be working with. So every texture that we load will have a different ID number here. We also have a member variable here for the pointer to our error handler. We have a pointer to our image data. This is where all of the color data that we're loading in will be residing. And then we have a width and a height, so that's the size of our image, and a color type. And then we have the bottom here. Now, color type we haven't defined, so we need to create a structure for that. Actually, it's an enumeration, and I'll do that right here at the top. So as you see, we have two different color types. We have red, green, blue, and red, green, blue alpha. By default in the constructor, you'll see I'll set every image to be red, green, blue, and then in the load function, we'll see if we have an alpha channel in the texture, then we'll change the color type to be red, green, blue, alpha. Let's save that .h file, and now let's work with the .cpp. Okay, as I mentioned earlier, we have our constructor with error handler pointer getting passed into us. So we take that pointer and we save it in our member variable. And the constructor's responsibility is to initialize all of our member variables to something. So we set our image data to be null since we don't have any data yet. And we set the width and the height and the bits per pixel to 0. The unsigned integer ID number we also set to 0. And as I mentioned before, we set the color type to be red, green, blue. In our destructor, we need to deallocate any memory that our class creates. Now, you haven't seen us create any memory yet since we're not working with the image data yet, but here you can see that if we have image data, in other words, if we've loaded something, then this is going to be true since in the constructor we set it to false. So if this is true, we then go and call safe_delete_array. Now, we haven't defined what safe_delete_array is yet, so let's go do that before I forget. If we go into the core.h file, you'll notice that here we have safe_delete, and right below it I just place safe_delete_array. What it does is it's basically the same thing as safe_delete, but it's working on an array structure. So we have this extra bracket right here between the delete and the value that we're trying to delete. And other than that, it does exactly the same thing that safe_delete does. So that takes care of our safe_delete macro here. Let's take a look at the next function. Okay, here we have the load, and with our load we pass in a file name that we want to load. The first thing we need to do is determine whether this file name is valid. And the way we do that is we check the length of this file name and see if it's less than 4. If it's less than 4, then we automatically assume that the file name is invalid since we don't have an extension that's valid for our loading process. So if it's less than 4, we then use the error handler to set an error message saying invalid texture file name, and then we specify the file name that's invalid. We show the error message to the screen, and then immediately we set the error back to no error. Now, the reason why we do this is because we want our game engine to continue running even though a texture problem occurs. So, for instance, if we're trying to load some game and there's some missing textures, we actually want the game to continue running just without any textures. So this part here will facilitate that so that you can continue running. And then we return 0 so that we exit the load procedure. 0 is equivalent to false. Okay, if we go down here, we know that we have a valid file name, or at least we think it's valid. So what we need to do is determine what kind of file this is that we're trying to load. And the way we do that is we look at the extension of the file name that's getting passed into it. So we create some memory here, 5 characters, and we copy the last 3 values from the file name into this temporary variable. We convert this temporary variable to be in lowercase, and then we check to see if it's TGA. So for instance, if we passed into our file name here something like image.tga, then this would return true, which means it is equal to 0, and then we'll go and call load_tga. If the file name extension isn't TGA, then we just generate an error message saying game engine cannot load unsupported image file. And we just do this because currently we only have this load_tga function. If you go and create other file loaders, we would then have extra if statements down here to specify, is this like a JPEG, is this a BMP, and so on. Okay, now the next part is the load_tga function. Before I go and show you the load_tga function though, I'd like to describe to you a little bit about the TGA file format. You need to understand this file format if you want to create a load function. So to do that, let's go take a look at the TGA file spec. If you go to whatsit.org, www.whatsit.org, you'll find this very handy website. It has a listing of different kinds of media files, 3D files, and so on that you can go and read about so that you can get more information on. Now we're interested in TGA, which is a graphics file, so we'll click on graphics file on the left here, and it'll load up a page showing you the different kinds of graphics files that you can read about. Now you'll see it's listed alphabetically, starting with A, and it goes down. Here's BMP and CDF and so on. And TGA happens to be on page number 9. So we'll click on page number 9 and wait for it to load. And if we scroll down here, you'll see under the TGA section there's 2 downloads. The second one is the TGA file format specification version 2.0. It's an Adobe Acrobat file. So if you download this and take a look, you'll see you'll have a zip file with 2 files within it. One of the files will be this Adobe file here, TGA file format. Have a read through this document and it'll describe to you exactly how everything is saved in a TGA file. You can see that there's different descriptions on the definitions for what this document contains, and then you'll see that here's an overview of the TGA file format. You'll see the first piece of information in the TGA file is 1 byte long, and it's the ID length. Then there's another byte for the color map table, and so on and so forth. The image data, which contains the color map or the pixel data, is stored right here. That's mainly what we're interested in. And if you go reading through here, it tells you what each of the fields represent. So after reading through this, you should have a very clear understanding as to how a TGA file is stored. So after knowing that, we can then go and create a load TGA file function. And here it is. So first thing we need to do is we create ourselves a TGA header. And what this TGA header will do is hold the information in the TGA file that's contained in the first section here. So it's going to contain the ID length, the color map, the image type, the color map specification, and the image specification data. And it's very important in which order you create the structure called TGA header, because it has to match exactly the same structure that we have in the TGA file. So let's go into the .h file here and take a look at that structure. As you see, the very first item is ID length, then we have color map type, image type, color map specification, 5 characters, and then we have X origin, Y origin, image width, image height, pixel depth, and image descriptor. Now, all these items here happen to be grouped into image specification of 10 bytes. I just broken them down further because if you look on this page here, image specification, here's the X origin, Y origin, and so on. So I've just broken these down immediately instead of having one variable for this and then having to break that down further. So that's all the data. Now, just because we create this data structure here, right here actually, that doesn't mean this data structure has any information in it. We have to load the information from the file into this data structure so then we can use it. So to load something from a disk, we need to create a file stream. And we do that using std-ifstream. And I'm going to call this stream TGA file. I pass to it the file name that I want to be loading, which is the same file name that got passed into our function. And I specify here, using the scope resolution, that we're going to be opening the file in binary format. We can also open it as an ASCII format, but that's not how a TGA file is stored, so you need to make sure you specify binary here. We check to make sure that the file was opened successfully. If not, we generate an error message here saying cannot open this specific file. We show the message and we generate, we clear the error message then, and then close the TGA file, we return false. So that's if there's an error. If there's no error, we continue on through. So here, we go and call read on the file stream that we have open, and we specify we want to read the data of the TGA file. We dump all the data that we read into our local variable here, TGA header, and the amount of data we want to read is equal to the size of the structure. So that's going to fill up this entire structure with data. If it fails, again, we generate an error message saying error reading this header, show the error message, and so on. You'll see we repeat this process anytime that there's an error message. But if we succeed, we just continue on down. So by the time we get to here, we've loaded the header information. So now we can use the header to determine whether this is the right TGA file or not for us. We're only going to be allowing two different kinds of TGA files. If you go back to the specification document, you'll see under the image type, we've got some numbers that are associated with what kind of TGA file we're loading. Well, we're only going to allow true color images. So there's an uncompressed true color image, which is a value 2, and there's also a run length encoded true color image, which is a value 10. So in our code, you can see if this image type is not equal to 2 and it's not equal to 10, then we generate an error message saying that we don't support this specific TGA format. Otherwise, we continue on through. Okay. When we get down to here, next we check to see the pixel depth. Well, we're only going to allow either 24 bits per pixel or 32 bits per pixel. 24 means we're going to have red, green, blue channels, 8 bits per channel. Or if we have 32, then we're going to have red, green, blue, and alpha with 8 bits per channel as well. So if neither of these are in our TGA file header, then we again generate an error message saying we don't support this specific color depth, and then we just show the error message and quit. Otherwise, we continue on through. So down here, we check to see if our bits per pixel is equal to 32. If it is, we need to change the default type to red, green, blue, alpha. In the constructor, you'll notice that we set it to be red, green, blue. So by default, it's going to be red, green, blue. But if the number of bits per pixel is 32, we change it to be red, green, blue, alpha. Okay. Next thing we do is we create this local variable called unsigned integer bytes per pixel. And the number of bytes per pixel is equal to the number of bits per pixel divided by 8. So number of bytes, there's 8 bits in 1 byte, so we just do a little conversion here. And we need this because all the following procedures will be requiring the number of bytes per pixels rather than bits per pixels. So it's important to have this variable. Okay, then we start checking to see the file size of this texture that we're loading. Well, the file size is actually stored in the header, so we can just extract the width and the height from the header data and put it into our member variable for the width and the height. If the width is not equal to the height, then we generate an error message. Now, we generate this error message because we're only going to allow images that are square in size, meaning the width has to equal the height. If this isn't true, we're going to generate this error message here saying cannot load the specific file, size must be square. The other requirement that we have on the size is that the dimension has to be equal to 2 to the power of some number. So for instance, it has to be like either 2, 4, 8, 16, 32, 64, 128, and so on. It has to be one of those values. If it's not, then we're not going to allow that texture to be loaded and we're going to generate an error message. So to check for that, what I do here is I go into a little loop and we check to see whether the size, we're checking the width, which is equivalent to the height if we've gotten here, and check to see if it's equal to this value here, UI size. So we started off at 1 and we keep multiplying by 2 while checking this width. If it's equal, if the width is equal to this special numbered size, then we change our variable here BOK to be true. Otherwise, it's false by default up here when we declare it. So after going through this while loop, we'll know whether BOK is okay or not okay. If it is okay, then that means that our size for our image is the correct dimension. It's 2 to the power of something. If this returns false, then we know that we have an error because the image itself is not square and it's of the wrong size. So for instance, we might have something that's square. It could be maybe 13 pixels by 13 pixels, but that's not valid because we only either accept 8 pixels or 16 pixels. So if you wanted an image that's 13 by 13, you'll have to save it in a file that's equal to 16 by 16. So just buffer it with some black pixels or white pixels or any other value that you like, really. So there's the error message that we generate if we have an error. Okay. So when we get to here, we know we have a texture that's of the specific bits per pixel that we allow, and it's the correct size. Knowing that, we can allocate some memory that will contain all the data that's inside the file. And to do that, we take the width, multiply it by the height, and multiply it by the number of bytes per pixel. This gives us the amount of memory we need to store the image that we're loading from the disk. So that value is going to be stored here in UI image size. So we use the new operator to create some new memory, and the amount of memory we require is based on what we calculated up here above. If this memory cannot be returned to us, then we generate an error message saying, cannot load this image, not enough free memory. So we then continue on if there's no error message. And before we can read in the pixel data, we need to do one last thing. We need to check this ID length, which we loaded up in the header, and check to make sure that we offset our current read pointer by the number that's stored in the ID length. If you go back into the technical spec, you'll see here the ID length field identifies the maximum bytes contained in field 6. And if we go through here, you'll see that field 6, 1, 2, 3, 4, 5, 6 is this image ID section. It could have some data. So if there is data here, we need to make sure we can skip over it to get to the next section, which will be image data. We don't have to worry about the color map data since for our specific file types, this will always be 0. If you read through the document, you'll see any true colored image will have the color map data equal to 0 in size. So we don't worry about that. We only have to worry about this image ID. So to skip over that data, we use the seekg command, and we go and pass in the length here, and we say we just want to offset the current position by however long this is. If it's 0, it's not going to move it. If it's some value, it's going to move our current pointer of our file. Okay, now we've got our pointer to our file stream pointing at the very first pixel data that's in the file, and we're ready to load in our data. We're going to be storing the data in this member variable here. However, we may need some temporary variables while we're reading in from the file, depending on whether the file is compressed or not compressed. So let's take a look at the case where the file is compressed. So if the image type is equal to 10, then we know we have a run length encoded file type. So we need to go and uncompress the data and then save it in this variable up here. Okay, the first thing we do is we create some local variables here which we'll use to determine how to save the data in our member variable. So we create a counter which is going to point to 0 initially, and then we're going to keep moving it every time we load data. We have a while loop here which will go through all the data while the counter here is less than the width times the height. So in other words, the counter is used to point to every single pixel in the compressed file format. First thing we need to do is get the repetition count value. And again, if we go into the file spec here, near the very end, you can read about how run length encoded images are stored. And you'll see that there's two different kinds of packets. There's a run length packet as well as a raw packet. And so what we're going to be working with down here below. So we read in the repetition counter value, and we store that into the temporary count variable. If there's an error, we just generate it, and we return. We then take that repetition counter value, and we check the highest significant bit. If it's on, meaning it's true, then we have a run length packet. Otherwise, we have a raw packet. So if we have a run length packet, we need to take that temporary counter value and we mask that initial highest significant bit by a 0. So we see here we have 7F, and then we add 1 to it according to the spec. We then know how many times we have to repeat the value that we're going to be reading in next. So we read in the next pixel, which is right here. We read in the 1 byte per pixel, and we store it into our temporary data variable here. After reading in that value, according to the run length packet encoding, we have to take that pixel value, which is here, and copy it for this many pixels. So in other words, this pixel is repeated this many times. So we go into our member variable. This is where we're going to be storing our image data, and we go through this loop and we continually save that data that we just read into our member variable here. Now, instead, if we're talking about a raw packet rather than a run length encoded packet, then we take the temporary counter, we add 1 to it. We don't need to mask anything because we know that the highest significant bit is already 0. Now, what we do is we read in some pixel value into our temporary variable. However, we read in the number of bytes per pixel times this counter. Again, some error checking here, and then after we've read that in, we just copy all that data that we've loaded in here into our member variable, which is shown here. So, in other words, we're taking everything here and we're dumping it into our member variable, and the amount that we're putting in there is the number of bytes per pixel times this counter up here. And the last thing inside this while loop, we just increment our counter so that we can go and read the next pixel of data. Okay, so that's how we handle compressed data. However, if we don't have compressed data, then reading in the image data from the file is actually relatively easy. All we need to do is we say, please read in this amount of data, which again is the width times the height times the number of bytes per pixels, and we place it right into our member variable data since it's not compressed. If that completes successfully, we're done. If not, then we go and do some cleanup. We then, when we finish reading in all the data, we can then close our file stream since we're not going to need it anymore. We're almost done with the texture data. However, we need to go massage it a little bit. So the first thing we need to do is we need to convert our data that's stored in our member variable here, and we need to swap the blue with the red, because a TGA file actually saves data in this format, blue, green, red. However, OpenGL needs the data to be stored red, green, blue. So we need to flip the blue with the red so that we get red and green and then blue. So to do that, we create a temporary variable here, which we'll use to store the value that we're going to be swapping, and then we go through the loop through the entire size of the image, and we swap out the blue with the red. That's just a swap routine. Then the last thing we do is we check to see if our image is flipped. It is possible that our image is either flipped horizontally or vertically or both, and that data is stored inside the image descriptor. And again, we go into our file specification here. Let's see if I can find it here. You'll notice that the image descriptor, bits 5 and 4, will tell you which orientation the image is in. So if the home position is not at the bottom left, meaning 0, 0, then we need to flip it. So if it's at the bottom right, we need to flip it horizontally, flip it in the vertical plane. If it's in the top left, then we need to flip it in the horizontal plane. And then if it's in the top right, then we need to flip it in both. And I drew a little image here to show this a little more clearly. So this is the original file that we want. However, it's possible that in the TGA file format, the image is actually stored this way. So if this is the case, we need to take this image and convert it so that it looks like this. And the way we do it is by flipping everything in the vertical plane. So we take this pixel and we flip it with this one. So in other words, we just swap these two. We then go through the entire image, flipping everything from the left to the right. If the image is stored like this instead, and we want it to look like this, then we need to flip everything from the bottom half to the top half and vice versa. So we flip everything back and forth this way. However, if the image is flipped in both axes, then we need to operate on it both in the horizontal and the vertical. And let's go through and take a look how we do that. So we check to see if the image is flipped, and if it is, we set this variable here to be true, either the horizontal or vertical or both. And then we check to see if either of these are true, and if they are, we call flip image. and then after that we just return true, saying that our image has been loaded successfully, we're ready to use it. So let's take a look at the flip image function. Okay, let's take a look at how the flipping works. First thing we do is we create a temporary variable which is the size of 1 pixel. We call it UCTemp, and then we check to see whether we need to flip all the pixel data according to the vertical line or according to the horizontal line. So again, if we go back here, we see if we're flipping on the vertical line, we're going to move across horizontally, and then if we're flipping on the horizontal line, we're going to be moving vertically. So if we're moving horizontally, we're going to be flipping on the vertical line, and we have the 2 nested for loops here. So we're going to be going over the full height and only up to the half width. And then as we're going through, we're going to be taking the data from one item and flipping it with the other item on the other end. So here's the code for how we do that. And the same procedure is done for flipping on the horizontal line. So if we have to move vertically, we're going to be flipping on the horizontal, and again we have a double for loop. So this time we're going for the full width and only the half height. And again, the flipping is exactly the same as up above. Okay, and then after we finish doing the flipping, we then have to delete the value here for this temporary member variable. Okay, we only have one last function to take care of. The last member function, create texture OpenGL, I'm going to leave blank for now because if I were to show you what happens inside here, you might get a little confused because we didn't talk about the scene yet. So in the next VMK, when I talk about how to change the scene class, we'll come back here and write this create texture OpenGL. Let's save all this work and see if we can compile. Okay, we have some errors, and all these errors are related to the file stream. So we need to go into stdafx.h and include one thing. Okay, we include fstream, and that should have all the items declared that we need. Let's go and try compiling again. Okay, so now it succeeds. So we're now ready to go and change the scene class. So come back for the next VMK and I'll show you how to do that.